graph, we have the parent function, and we're going to write all of these things about it. And then next to it, you have a different function where they've put in different a, h, and k values. And so we'll make sure we can graph the absolute value function and then go through these things correctly. So since you guys are pretty good at graphing, why don't we go ahead and do both of the graphs first? And then if you think that you know the answers to some of the things below them, go ahead and start filling them in. So how about we give you guys like 7 minutes or so to do the 2 graphs and as much as the chart as you think that you understand how to do as of right now in your understanding of absolute value function. And maybe put a little star or a little dot next to the words in this chart that you feel like you don't know what that's referring to. Is that good with everybody? Okay. You can talk to the people in your group. So let's pause for a second and talk just about the graphs, because the majority of the people are done with the graphing portion, and then I'll let you guys talk to each other again about some of the words in this chart surrounding the graph. So the parent function, most people seem to have correct. Okay? You have your vertex here at 0, 0. The lines have a slope of +1 or -1, and the v is facing upward. Okay? What about for the graph that's next to it? So when we start having some different a, h, and k values, how did you guys start your graph? Where did you decide to start? Caden? Okay, and so what did you get as the vertex? 2, 6. Okay, so we keep using this language, so I feel like we're a little familiar with this. So the vertex is 2, 6, and she's getting that by picking out that h and that k value from the equation. Is everybody okay with why it's +2 and +6? So my vertex will be at 2, 6. All right, which way should the V open? Yes, down. Okay. And what should the slopes of the lines be? Now, I know one's positive and one's negative, but numerically, what should their slopes be? Yeah, Andre. Okay, so negative meaning it's facing down. But remember, it takes 2 sections of line to form the V, because the lines are going like this. Technically, one has a positive slope and one has a negative slope. But what's the numerical value of the slope? Jonathan? Good. So the rise runs are the 2/3 right here. So the 2 is the movement down, and then 3 either right or left, depending on which branch you're trying to draw. So from this point, down 2 over 3, okay? And then down 2 over 3 the other direction to get my branches of this. Okay? All right, so I'm going to let you guys get back to working. Okay, so the parent function is simpler just in the way that it's oriented on the graph. And then the answers get a little more complicated when we carry them over into the other, because we've moved in and shifted in, changed the slope and all this kind of stuff. So vertex, you guys have already been using that language and are aware. So that's the point where something usually turns around. We'll kind of loosely use that term with some other shapes that don't technically act like a parabola or an absolute value function, but we'll still call that like 0, 0 starting point, like our vertex, just so we have a way to communicate about it. Okay? But in this case, so 0, 0. So what is the x-intercept or x-intercepts of this graph? Jolie? Good. So it hits the x-axis at 0. What do x-intercepts always have in them? Let's say I didn't show you any graph, and I said, I want you to tell me, like, you just have to have, like, ESP or, like, telepathic communication or something. What's going to be the x-intercept of the graph? One part would be completely unknown to you, but one part should be known. What should you know? Natalie? Good. That y is 0. If it's an x-intercept, it's on the x-axis, right? That forces the y-coordinate to be 0, because if the y-coordinate's not 0, then the point was shifted up or down from the x-axis and would no longer be on it. So for every x-intercept, you automatically know the y-coordinate is 0. Okay? And for y-intercepts, what do you automatically know? Olivia? Good. X is 0, or else it wouldn't be on the y-axis. So we know this automatically. That should help us list points, should help us understand it visually, and it should help us if we want to plug in and do something algebraically. If someone uses the word intercept, they are telling me a value I could plug in and then find something to go with. Okay? So in this case, both of these are 0, 0, because it hits the x and the y-axis at the origin where they meet. Okay? We'll talk about how to solve for them when it's not that apparent or when it's more difficult to see where they are hitting. Okay, what is the domain of our absolute value function? Yeah, Brandon. Good, all real numbers. And so I'm going to write it in interval notation. So that's from negative infinity to infinity, if you want to make a note that that's all real numbers. Okay. And this is specifically referring to the x values of our equation, for those of you that still struggle with what is domain versus what is range. What is the range of this function? Jonathan? Okay, so 0 and positive numbers. So how can I say that in interval notation? Olivia? Good. So it goes from 0 to infinity, but it hits 0, right? Another way to say this that we would be used to saying would be that y is like greater than or equal to 0. Okay? It might be useful for you to still write this other notation over here, because if you're still struggling with how to write this and what this means, it's going to help you to see things that mean the same thing, right? You can write both on the test if you want. You can write either on the test for right now. Later on, I'll ask you specifically to write interval notation, or like when we talk about these, we specifically write intervals, and then there you have to use the intervals. But for domain and range for right now, you could write either one. Okay? All right, so increasing intervals and decreasing intervals. We read a graph like we read a book. Okay? We read it from left to right. Okay? So if I'm walking along this function across the graph from left to right, okay? At first, as I'm walking along the function, am I increasing or decreasing? Decreasing. As the x is going this way, the y values are lowering. So this branch of the graph, don't be confused because the arrow's pointing up here. If you read it from left to right, it's going like this, right? So from forever until here, where I turn around, the graph would be considered decreasing because the y values are falling as you're reading that graph. Okay? But when you write the intervals for these, you describe them using the x values. So this is a little confusing for people, because when I'm looking at if it's increasing or decreasing, I'm thinking about what's happening to the y values, right? As I'm going, the y values are getting lower, so I call this decreasing. But when I describe to somebody which part is decreasing, the numbers I write here are telling them which part of the graph I was reading from left to right. Okay? So that's referring to the x-axis. So this graph was decreasing from forever, right, until I got to where? 0. So this whole time, infinitely this way until 0, the graph would be decreasing. So from negative infinity until 0, the graph is decreasing. Now at 0, the graph is kind of both part of the increasing and the decreasing part. So we just put the parenthesis and don't include 0 for sure as either or, because it's like the point of turning. Does that make sense? So you don't categorize it in either way. It's just like this place where it's in between. Okay? Yes? Oh, sorry. Thank you. At least somebody's paying attention to what I'm doing. I was so excited about explaining it that I didn't look where I was writing it. Sorry. I hope you guys have a pencil. Okay. All right. Good? Yes? No. So you do reach 0 on the graph, but is the point at 0 part of the increasing or the decreasing part of the graph? Yeah, I don't know either. It's the point where it turns around, right? It's the point where they both meet. So that's why we don't include it there. Does that make sense? Okay. So the turning point gets excluded when we're talking about increasing and decreasing because we don't know which one to categorize it as. All right. So then, as I move across the graph from 0 towards infinity, okay, the graph changes directions, and I would be going like this, okay, which means as I am going from 0 towards infinity across the graph, the y values of the graph are increasing. So increasing describes what's happening to the y values, and then I'm telling them which part of the graph they would read to see the increasing parts by listing x values. So I would say from 0 to infinity, it is increasing. I didn't include 0 in that one either, again, because 0 is kind of the point where they meet and is the turnaround point. So for the next part, the one-to-one thing, first of all, is the absolute value a function? does it meet our function requirement? Yes. Okay? And so to be a function, we say every x value has to have one y value, right? So this x goes to a different y. So there's not this. Same x going to two different places. That would make something not a function. So the absolute value is good in that respect. Okay? These points still meet the function requirement. It's okay that they both went to 1 because they had different inputs, are okay to go to the same output. Okay? But 1 to 1 is the other side of like being a function. Not only does every input have one output, but every output only goes back to one input. So is this function 1 to 1? It is a function. It meets that requirement. Is it 1 to 1? Does that same rule work the other way? For every y value, is there only one x value that it matches with? Well, look, here's a y value of 1. I can get that from an x value of 1, but I also get a y value of 1 from negative 1. So is this function 1 to 1? No, it's still a function, but it doesn't have it working the other way too, where all the outputs only go with one input. Okay? So it's not 1 to 1. Okay. For rate of change here, we're just going to be referring to the slopes of the lines. So for the parent function, what is the rate of change for each branch of the absolute value function? 1. Okay, different direction, but the rate of change is 1. What would be the axis of symmetry? Connor? Good, it's at 0. Is it a vertical line through 0 or a horizontal line through 0? Vertical. What is the equation for vertical lines? X equals 0. So you might not think that's important, but we're going to start dealing with things that have all different kinds of axes of symmetry or asymptotes, which we'll talk about in a minute. So it's important that you label them with their full equation so that we understand if they're horizontal or vertical lines. Do you have a question, Doc? No? Okay, what is the minimum value? So minimum value is specifically talking about a y coordinate, if it's minimum or maximum, because that's up or down on the graph. And they just want that one value. What is the highest value they reach, or what is the smallest value that they reach? Okay? So what is my minimum value? Caden? 0. And it's just one number. It's just 0. Okay, but because by saying minimum value, they already know it's the smallest. And by saying value, if a person reading it understands mathematics, they know that we're talking y-wise and that that's the smallest thing it reaches. So it's just a single number, okay, a value. What is the maximum value? Josh? Yeah, so there really isn't one, okay? So there is no maximum, so we're just going to say none, but infinite is the right idea, okay? So asymptotes came up. I was talking with a couple of people around the room about these. So the only place you guys would have probably seen these before is when you studied exponential functions. So the way that exponential functions work is they generally grow like this and they decrease like this. And they basically get closer and closer to this one value, but they never, ever touch it. So that's kind of a hard idea to understand, but then we can contextualize it a little bit and make sense of it. For example, if I'm going to walk from the back of the room, from the front of the room to the back of the room by cutting my distance in half every single time, okay? So let's say I'm 20 feet from the back of the room right now, okay? If I cut my distance in half, how far will I be from the back of the room? 10. So I'll go from 20 feet to 10 feet. Then how far will I be from the back of the room? 5. Then how far? Then how far? Then how far? So physically, I would eventually run into the wall. I'm not a small person, okay? I'm going to hit the wall, okay? But theoretically, will I ever reach the wall? No. I'll be like 0, 0, 0, 0, 0, 0, 0, 0, 0, something, but there will be something, right? So it's like this weird idea in math that you're getting closer and closer to this value, but you never reach it. It's weird because there's always infinitely many numbers between two things. Like if I asked you guys, how many numbers are between 0.8 and 0.9? How many are there? You want to blow a little kid's mind? Ask them that question. Right? How many numbers are there between 0.8 and 0.9? Infinitely many. It's so crazy, right? That there's infinitely many things in these little teeny sets that we just draw like this on a number line or something like that. So that's where the asymptotes come in. This function doesn't have any of those properties. Okay? So both of these are none. It does not have either one of those things. Okay? All right, so let's look at the example that had some other values in it, and then I specifically want to focus on the intercepts. So I'm going to save those for last. So we'll quickly go through the list, and then we'll spend a little time with intercepts, and then we'll talk about your homework from last night. Okay? All right, so we're going to come back to the intercepts. Domain, who can give it to us? Jonathan. Good, all real numbers. Okay, so written in otherwise all numbers. Range. Yeah, Claire. Okay. Good. All numbers less than or equal to 6 or just less than 6? Good. All y values less than or equal to 6, okay, which means 6 is the biggest and it's everything below it. So 6 is the biggest, but it's forever below it. That's a parenthesis and that's a bracket. Okay? Increasing interval. Any ideas? Mia? Good. From negative infinity until 2. Okay? Because as I move from left to right, I am increasing from forever to the left until I get to this point, which is at an x value of 2. Okay? What is my decreasing interval? Megan? 2 to infinity. Good. 2 to infinity. Is the function 1 to 1? No. So you guys run a vertical line test to test if something's a function, right? So it would have to pass that test to be 1 to 1, but it would also have to pass another test. What would the other test be? A horizontal line test. It would be like going across here and making sure there was only one point lined up for every one of those. So if it passes both tests, you could call it 1 to 1. That's the idea that we're looking at, okay? So this one, 1. What is the rate of change of the lines that form our absolute value function? Andre? Good. Okay. And you can put 2/3 or negative 2/3 because remember, the absolute value graph, remember when we wrote it as a piecewise function? It consists of 2 separate linear functions. One has the positive numerical slope and one has the negative. So we're really just looking for the number here. I'm not going to mark you wrong whether it's positive or negative for these functions. Okay? What is the axis of symmetry for the function? Jonathan? Good. X is equal to 2. Okay. Minimum value. Conrad? None. Good. Maximum value. Jolie? 6. Do we have asymptotes? No, not in these situations, right? Now, you guys probably could have pulled a lot of your intercepts off of the graph, but there's an important idea here about solving absolute value equations. Now, the y-intercept is hard to tell, right? Okay, so let's start there. If it doesn't cross exactly through one of the points, it's a little bit hard to tell exactly what the intercept is, and this is when you need your algebra. It's like solving the systems of equations like we talked about before. Graphing is only a really useful thing if they happen to cross at this nice little place on the graph and it's easy to tell. But if not, we need substitution and elimination to give us those exact values that we can't see with our eye on the graph. I feel like the y-intercept here is another one of those situations. I can see it. I get that it's something bigger than 4, smaller than 5, closer to 5, okay? But everything after that would be me just kind of guessing. Okay? So what algebra could I do to get the exact value and know that I was correct? Brandon? Okay, so we could write the equation in slope-intercept form, but we do already have an equation that represents this entire graph. So if we already have an equation that represents this entire graph, how am I going to get that y-intercept value? Natalie? Good. So if we're specifically looking for the y-intercept in this case, what are we plugging 0 in for? X. Because to be on the y-axis, the x-coordinate has to be 0. So remember, again, we already know a couple of things here. And those things translate into algebra I can then go do and figure out the other. So for the y-intercept, I'm going to plug 0 in for x. Okay. So I have negative 2/3. So 0 minus 2 is negative 2, but what is the absolute value of negative 2? 2. So this is just 2. So I get negative 4/3 plus 6. I'm going to think of 6 as 18 over 3 so that there's a common denominator. And that gives me 14 over 3 as my intercept. And then I can see if that makes sense. Okay, how many times does 3 go into 14? 4 times with 2 left over. So does 2/3 make sense on our graph as an intercept? Yeah, it all kind of fits together, right? So that's good. Any questions about how we solved for the y-intercept? So the equation can get crazy and weird, but it never changes the fact that if you plug in 0 for x, you're getting the y-intercept of whatever this graph is that you're trying to create, absolute value or not. Okay. All right, so what about the x-intercept? So you guys can see them on your graph pretty clearly, but you can tell you might run into a point where you can't see them on your graph clearly, right? So what are you going to do then? You're going to do this same process, but what change are we going to make? Julie? Good. Plug the 0 in for y. So if I go through this same thing, but I plug 0 in for y, this is a little bit trickier. Okay, so the first thing I'm going to do, and this is going to be a pattern with a lot of our functions, I am going to try to isolate the part that contains x. What I mean by that is x is part of this stuff trapped inside the absolute value, and it functions a certain way. I need to get that piece alone so that then I can deal with exactly how absolute value functions. Okay. So the first thing I'm going to do is subtract 6. And then I'm going to multiply each side by the reciprocal of this fraction so that it would cancel out. So I'm going to multiply by negative 3 over 2, because negative 3 over 2 times negative 2 over 3 is just 1. But I have to do the same thing on this side. So just kind of off to the side a minute. If you guys came in today and I had said this, what number could be inside the absolute value bars to make that a true statement? Casey. Negative 4 or 4. So are you guys on board with the fact that if somebody told me the absolute value of something equals a positive number, I have 2 choices for what this thing could be in here? Okay? Now, if they told me it equals a negative number, what are the answers to that? Not possible. So if your v, if we shifted this whole thing down here, what would the x-intercepts be? They would be non-existent, and algebraically you would see something like this that doesn't make sense. You would be trying to get an absolute value set equal to a negative number. So be aware of that, okay? But an absolute value can definitely equal a positive number, but there's 2 ways that it could equal a positive number. This stuff inside the absolute value is either 9, or this stuff inside the absolute value is negative 9. Both of those things work. That is why your graph is having 2 x-intercepts. There's 2 ways that this can happen. It's why it's not 1-to-1, right? So either x minus 2 is equal to 9, or x minus 2 is equal to negative 9. Okay? So this is a characteristic just of absolute value. Okay? We're doing this because we understand how absolute value works. It gives us 2 options for what could be inside of there. And so that means it could be x equal to 11, or it could be x equal to negative 7. Connor? No, that's the first problem. We said this can either equal positive 9 or negative 9, because once you take its absolute value, it'll turn it positive. Is that okay? So we have 2 x-intercepts, one at 11, 0, and one at negative 7, 0. It makes sense with what the picture looks like, okay? And why we can do that with absolute value, right? And that it's not 1-to-1. Is this okay with everybody? So on your test, when you're given a function to graph, you will be asked these things right here, okay? Do these things make sense to everybody? Okay? Yes. So the asymptotes here are always going to be none, okay? And that's all you have to remember for this. I might even take that part off of here because we're going to get to exponential functions like you guys did in Algebra 1 and study them again and a little bit deeper. And we're going to see a logarithmic function that also has some asymptotes. And we're going to deal with them when they're important. They're just not important here. They're important in math, just not when you're dealing with an absolute value function because they kind of have nothing to do with it. Is that okay for now? Okay. Everybody good? Yes? All right. So